Is it fine now? Oh.
There are three menus on the top of your screen. In the middle, you see display settings. Can you click on that?
Yeah, they changed actually.
Oh, the menu doesn't open. There's a little triangle next to the display settings. Can you click on
Yes,
that?
I tried it.
Now it's
Okay.
Great.
Okay.
Yes. Thank you, Maximilian.
Yeah, sorry for the delay. So thank you, Luis, for your kind introduction. And thank you, the organizers, for giving me the opportunity to share my results here. So as Piotr in his talk indicate, I will be going to talk about magnesium alloy anode in magnesium batteries, specifically ductile magnesium alloy anodes. So I'm a PhD student at Denmark Technical University. And the motivation, so as you can see, so the formation of the passivation layer is one of the well-known problem in magnesium batteries. So when the magnesium metal anode come in contact with conventional electrolyte, it always creates a problem of formation of a passivation layer, which is impermeable to the magnesium ions. And there is two solutions actually to bypass this problem. The first solution is using intercalation or conversion type anodes. So basically the normal intercalation anodes use the bismuth, antimony, tin or indium. But the problem with using this type of anode is like one of the biggest problems is the volume change associated with this type of anode. As well as the other thing is that in order to exploit the energy density of a magnesium battery, we should use magnesium metal in its elemental form. Then only we can completely exploit the magnesium battery in terms of energy density. So the other solution is to use improved electrolyte. So that means like the APC or MAC electrolytes. Then we can use magnesium metal. But then the problem is like the magnesium has low ductility. So due to the external crystal system of magnesium is inherently brittle. So then the solution comes is we have to use a ductile magnesium alloy anode. So when I say is ductile magnesium alloy anode, it refers to a low dopant concentration. So the dopant concentration we added should be very low. Then only we can, as I said, we can completely exploit it in terms of energy density. So my work is basically on ab initio density functional theory investigation, which I made in search of ductile magnesium alloy anode. So the workflow is as follows. So the main aim of the work was to obtain a ductile magnesium alloy anode, and its electrochemical behavior should be similar or closer to pure magnesium. And the first step, we were screening the dopants, so the alloy. So first we were looking whether the dopants we added improve the ductility. Then we checked whether for that we actually started with 33 dopants, which already known to improve the ductility from the previous studies. Then we checked whether these dopants, whether these alloys are stable. After checking whether these alloys are stable, then we checked the electrochemical behavior of the magnesium alloy. So the alloy, the chemical behavior of the magnesium alloy should be closer to the pure magnesium. And for that, the first thing we have to study on the ductility. And here, what you see here, the main reason of the ductility is due to the insufficient number of planes for the deformation. So here what you see are the different slip system available in the HCP magnesium. And for magnesium at room temperature, only basal slip systems are available. But in order to accommodate the strain along C-axis, we need to activate the C+A slip system. And several studies indicate that the stocking fault in the structure can nucleate the C+A dislocation, which in turn activate the C+A slip system. So here what we are looking for the dopants which reduce the stocking fault energy on doping with the magnesium. So we compare the stocking fault energy of the pure magnesium with the stocking fault energy of the magnesium with the dopant, and we check whether the dopant reduces stocking fault energy. And when I say the stocking fault energy, there are mainly three types of stocking fault in magnesium, but the I1 intensity stocking fault is related to the ductility. So the I1 intensity stocking fault means it have a stocking sequence of AB, 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 AB. Then there is an missing of B plane, then it come AC, AC, AC stocking sequence. And the work of Sanlop et al. Shows that this intrinsic stocking fault have correlated to the ductility of the magnesium material. And the stocking fault energy normally calculated in ab initio or DFT calculations using this equation. So basically the first equation indicates the energy of the structure with an stocking fault, and other one, this EHCP is the normal HCP system and divided by the area of the stocking fault. But to computationally calculate the stocking fault energy, the energy of the stocking fault structure, it's computationally very expensive because we have to calculate the stocking fault structure. And since we are evaluating the 33 dopants, in this work, we used an axial next nearest neighbor Ising model. So in which each stacking sequences are represented with some spin number SI, SIN, and a interaction parameter is defined between them. Then this results in the stocking fault energy as like so. Then it results in like 2 times EDHCP minus EHCP. So here we can get the stocking fault energy just in terms of two bulk structures. So which is the HCP structure with AB, AB, AB stacking sequence, and a DHCP structure with AB, AC stacking sequence. And then we evaluated whether this doping give beneficial, did it reduce the stocking fault? So we evaluated based on this term, and the results are shown in this figure. So based on our calculation, you can see most of the elements have reduction in stocking fault. So that means these elements reduce the stocking faults and in turn improve the ductility of the magnesium. And we see like around like 5 or 6 elements which increase the stocking fault energy. So normally these 33 elements we studied known to be like make the element ductile, magnesium ductile, but we expect like this discrepancy may be come from the low doping concentration we used in the study. So the doping concentration we used is 2.98% at 8% of dopant we used in our studies. So we think this discrepancy may come from the doping concentration. And the next step to check whether the alloy is stable. So this is calculated based on the energy of formation with the dopant in the bulk. And it is calculated using this equation. The first term indicates the energy of structure with the dopant. So this is the first figure. So we calculate energy of the structure with the dopant and the energy of structure without the dopant. And EX is the energy of the dopant, like the just energy of the dopant in its ground state. And EMG is the energy per atom of the pure magnesium. And thus we obtain the bulk energy of formation. And to an alloy to be stable, the bulk energy of formation should be negative. So you can see the results in this figure. And so the elements which which show a negative elements are like they're mostly stable. So almost 20 elements are stable if you look in, and most of them are rare earths. And the elements which are not stable are mainly first and second group elements which have a bigger atomic radius. This may be the reason that they are not soluble. And the other elements like hafnium, titanium, and zirconium, these elements are known to be less soluble. So this agrees with our study. And the final thing is we want to know the electrochemical behavior of this dopant. So this we evaluated based on where the dopant goes. So we want to know whether the dopant will go to the surface. So if the dopant goes to the surface, then there's a chance of the dopant to be react with the electrolyte, so which may affect the performance, electrochemical performance of the battery. So that's why we don't want the electrode to be at the surface, but we want the electrode should be in the bulk. So this is 2D schematic diagram. So when you have the dopant in the bulk, then we have a interface, the electrode interface we have a dopant-free surface. The electrode surface is dopant-free. So this surface is similar to the pure magnesium. So the dopant didn't have any role in the electrochemical behavior. So now we are going to analyze whether the dopant going to prefer to be in bulk or dopant prefer to be at surface. What we want the dopants to be in the bulk. And for that, first we analyzed which all are the surfaces present in the magnesium at equilibrium condition. We used the Wolff analysis to obtain the equilibrium shape of the crystal. And we considered almost 12 surfaces in the magnesium and calculated its surface energy. And we constructed the Wolff plot. And from the Wolff plot, it is clear that only 3 surfaces will be possible or present in magnesium at equilibrium conditions. So this is 001 and 10 minus 10 and 10 minus 11 surfaces. And you can see the area fraction of the each surfaces here. So then we further studied on these surfaces whether the dopant prefer to go to the surface or in the bulk. So this study was carried out using these structures. So when I say it goes to the bulk, there is 2 possibilities. It can be in the bulk or it can be in the stocking fold. So even the dopant prefer to be in the stocking fold, then it's like it's in the bulk. So what we want to avoid, we don't want these structures to be favorable. So these are the, so in the DFT calculation, we normally put a vacuum to mimic the surfaces. And we put 2 dopants on each of the surfaces. And then we calculate the energy of formation of all the structures. So the energy of formation with the dopant either in bulk or in stocking fold or in any of the surfaces. So using this equation. And this is a similar equation which used for the stable analysis. Then we compare based on these 2 equations. So these 2 equations are made from the formation energies. And this is delta E bulk means it should be like it's the energy of formation when the dopant in the bulk minus energy of the formation when the dopant in any of the surfaces. And for the stocking fold, so it's like the energy of formation in the stocking fold or energy of formation in the surface. So what we want any of these should be negative so that our dopant will stay inside the bulk. And when we studied the stable, so these are the elements, the 20 dopant which are known to be stable after our second criteria. And we observed like aluminium and most of the rare earths show promising results. So they show to be stay in the bulk. So these elements are favorable to stay in the bulk. That means we get a dopant-free surface when we alloy with these dopants. And this to the summary, in my work, I assessed the effect of dopants in magnesium alloy to use the ductile magnesium alloy based on 3 criteria. The first criteria to check whether it is ductile. So for the ductility, I checked based on the reduction in the stocking fold energy of magnesium. Then I look for the stability of these alloys. So for stable, it should be negative. The bulk energy of formation should be negative. And we identified out of the 33 elements we studied, 20 elements are stable with magnesium to form alloy. Then we study the electrochemical behavior. So when I say the electrochemical behavior, we look whether we can obtain a dopant-free surface for these alloys. So after evaluating based on these criteria, we got almost 11 dopants which show promising results. Out of that, like aluminum is only the non-rare earth, the rest of the elements are rare earth. And among these identified elements, so based on these identified elements, we also see a commercial alloy which is already available. So this is WE45 alloy. So which are this yttrium and neodymium and zirconium. So these elements are shown to be promising. The only element not in our list is zirconium. The zirconium was not in our list because zirconium was not soluble in magnesium. But several studies indicate that zirconium is soluble when it's added with the rare earths. So we definitely recommended this commercial alloy which can be tested to be used at ductile MG alloy anode. And this is a preliminary work for the alloy designing. So basically, if you want for the multi-component designing and everything, so this can be a starting point for the multi-component designing of the ductile magnesium alloy anode. And thanks for hearing me. Then I would like to thank my team at DTU, our group at DTU, as well as the eMagic for funding my project. Thank you.
Thank you.
Thank you, Esmovin, for the nice talk, actually guiding us to look at alternatives anodes, especially these alloys. We are looking forward for your manuscript, your publication on the topic, and also looking forward for the experimental work that we are performing currently in our consortium dealing with the magnesium alloy anode as an alternative. So far, I don't have any question in the QA chat.
I would have one.
Yes, please, Maximilian, go ahead.
Do we know anything about the fate of these alloying elements that you showed? I mean, if you have this WE45 alloy that you have shown, there are some elements inside. What would happen in a battery when you strip and plate from such an alloy? What happens to these elements?
Actually, I didn't check whether the phases of this commercial alloy. But when I tried to study for this, the dopant just binary alloys. So what we really wanted, we want the phases to be HCP or like stain HCP. So that is like right now, like people are studying the alloy with like AZ31 kind of alloys with aluminium. So actually, I really want to see whether which are the phases. So I actually didn't look into the phases. So yeah.
Okay. Luis, you are muted.
Thank you, Maximilian. Sorry. Meanwhile, I was muted. I think one question is coming. I think we had 1 minute to see. Probably is writing. Okay. Daniel Hodge say, thank you, Vincent. Did you consider twinning?
No, I only looked at intrinsic stocking, I1 stocking fault, so I didn't consider for the tuning. So there are other stocking fault defects as well, but as a consideration, so we already know the I1 stocking fault is related to the ductility. So we only consider the I1 intrinsic stocking fault for the current study. Because it's already related, so I think I answered the question.
Okay, thank you. As moving, just pay attention if any new question come in the Q8 chat. Let's thank again to you talk. Thank you for the great job, Moving. Let's move on to the next speaker.